Hello everyone. So in the previous session you have discussed about the knuckle joint. In this session we will continue our discussion on the joints. So in this session we will take up the quarter joint. Okay, quarter joint is used to connect two coaxial rods which are subjected to either tensile force or compressive force. So both the knuckle joint as well as the quarter joint are used to join two coaxial rods which are subjected to tensile force as well as the compressive force, whereas the couplings are used to connect two shafts which are rotating. So here these knuckle joint as well as the quarter joint are not used to connect two rods which are rotating. Okay. So if you want to join two rotating rods or shafts, you need to go with the couplings, and if you want to join two rods which are in tension or in compression, then you need to go with the knuckle joint or the quarter joint. Okay, so in the previous session you already dealt with the knuckle joint. So in this session we will continue our discussion on the quarter joint. As I earlier told you, a quarter joint is used to connect two coaxial rods. It should be coaxial. There should not be any misalignment, which are subjected to either tensile or compressive load. So these are all typical applications of the quarter joint, where you can use the quarter joint to connect what parts. So joint between piston rod and the cross head of the steam engine. There you can use quarter joint to connect piston rod as well as cross head. One end of the piston rod to other end of the steam engine, cross head of the steam engine. Then you can use the quarter joint to join two slide spindle and the fork of the valve mechanism. Then joint between piston rod and the tail rod or the pump rod, and then you can use the quarter joint for the foundation bolt. As foundation bolt also you can use it. So these are all some of the applications of the quarter joint. So here the principle of quarter joint is the wedge action. Okay, the wedge action is used as the principle of quarter joint. So wedge means something taper in section. Okay, something taper in section. So a quarter is a wedge shaped piece made of a rectangular plate. So in the side view it will be rectangular in cross section, and in the front view it will be made up of one side flat like this and another side wedge like this. Okay, a wedge action is the principle used in the quarter joint, because if you insert a wedge shaped member and if you just try to hammer that one, so it will tightly fit in the slot. That is what the concept of wedge shaped piece of the member. So there are essentially three parts of the quarter joint, as in the case of knuckle joint. Here also there are three parts of the knuckle joint. The first part is sleeve, or it can also be called as the socket. It will be solid in the section, and the sleeve will be solid in the section, and it will be having some slot, rectangular slot, to accommodate the quarter. And then spigot. The second part is the spigot. A spigot is again round member that is kept inside the sleeve, and then quarter is going to introduce. Okay, so there are three essential parts of the quarter: sleeve, spigot, and the quarter. Spigot, the sleeve will fit inside the spigot, something like this. Then a quarter will be introduced between the common hole, rectangular hole, and then if you try to hammer it, the assembly will be tightened. You can use the wedge shaped quarter, and if you hammer it, it will be tightened. Thereby you can have the assembly of the quarter joint. So while designing the quarter joint, we should know the type of stress developed in the parts of the quarter joint. So each and every part, sleeve will undergo what type of stress? Spigot will undergo what type of stress? Then quarter will undergo what type of stress? These things you need to know. For that you need to know, or you need to write the free body diagram. Okay, the free body diagram of all these. So in the figure you can see the free body diagram of the assembly quarter joint. So in the figure you just have a look at the force distribution along the sleeve and spigot as well as the quarter. By looking at the force, you just try to imagine the type of stress developed in that particular member. Okay, so if I take for example a quarter, as you can see in the figure, the quarter will be undergoing double shear because it will be having 3 different forces on either side. So it will be undergoing double shear. Therefore the force, the stress developed will be double shear. The formula to calculate the stress will be tau is equal to P by A, load by area. Similarly, sleeve and the spigot will be undergoing some crushing as well as some tearing and tensile load. Tensile failure may take place, or shearing failure may take place, or crushing may take place. Crushing in the quarter, shear as well as tear in sleeve as well as spigot. These are all the type of stresses you can expect. So you just have a look at the figure for the type of failure can happen, the type of shear stress, the type of shear, the type of tear, the type of the crushing. You can see it in the figure. Okay. Then if you just go through the basic formula, we know that stress is equal to load by area. Stress is P by A, load by area. We can just rearrange the term and we can write this equation as P is equal to area into stress. The load is equal to area into the stress. Take area to the other side, area into the stress. That is what the basic formula we know. P, load is equal to area into stress. The same formula you are going to find in your data handbook. If you just open your data handbook and if you go through the page number 65, in the page number 65 the equation starts from 4.16a. Okay, page number 65, equation starts from 4.16a, b, c, d, like that. You will find the same formula, P is equal to A into sigma. P is equal to A into sigma, where you need to concentrate on the area. You need to concentrate on the area. So here load is equal to some term into sigma. You will find load is equal to some term into sigma in the data handbook. Here that term will be the area. Whatever you want to write apart from stress is the area. In the right hand side, in that equation, whatever you are going to write apart from the stress, if you just forgot about the stress, the remaining term explains about the area. That means to say it will be the area of shear in the sleeve, area of tear in the sleeve, area of shear in the spigot, area of tearing in the spigot, area of shear in the quarter, area of compression in the quarter, like that. Okay. So this is how you need to substitute for the area, corresponding area, to get the formulas, and then using those formulas you need to solve the problem for its dimensions, or maybe for the load carrying capacity, or maybe to evaluate whether the design is going to be safe or is going to be a failure. So this is the design procedure to be followed while designing a quarter joint. So as we all know that quarter joint is used to connect two circular solid coaxial rods. The rod will be circular in cross section. Okay. Since it is circular in cross section, first we need to determine the diameter of the rod. Okay, depending on the diameter of the rod to be joined, we need to design the quarter joint. Okay, in between the quarter joint will be there, and both the sides there will be rods. We need to get the diameter of that first. Okay, so diameter of the rod can be calculated using the formula load is equal to area into stress, or stress is load by area. As I explained you earlier, I have taken load in the left hand side, area multiplied by the stress. Okay, so here I need to substitute the stress as the tensile stress of the rod material. Okay, so this formula I can find it in the data handbook, page number 65, equation number 4.16a. Using this formula, just try to calculate the diameter small d of the rod to be joined. Okay, then in the step 2, design of spigot and the quarter, we will be concentrating on the design of spigot and the quarter. Okay, so here the quarter will be under compression load, the quarter, and therefore here sigma c is used. Sigma c means compressive stress, P is the load. So apart from the stress, whatever is there is the area. D1 into T will be the area of crushing. Area of crushing. Okay, you can just have a comparison with the figure. You can get the area of the crushing. This also you can find it in the data handbook with this page number 65 and equation 4.16b. Calculate, try to calculate D1 into T, that is the area. Okay, to calculate separately D1 and T, use one more equation, that is equation number 4.16c. Okay, use this equation, then calculate D1 and T separately. Fine. So this is how I need to design for spigot and the quarter. Then design for the quarter. Again, this quarter will be subjected to crushing, which is inside the spigot and the sleeve, as well as the quarter will be subjected to double shear. Both stresses are going to appear. We need to consider the maximum possible types of stress could be developed in the member to design a particular member. So this is the maximum possible stresses can be developed in the member when it is loaded. Okay. So design of quarter for the shear stress, double shear, P, that is the load, is equal to 2B into T is the area of shear. B into T is the area of shear. 2, because it is double shear, shear will take place at two different parts. So double shear into the shear stress tau. So here tau is equal to P divided by area is the formula, shear stress formula. Area I have taken this side, so this is B into T is the area. 2 is for double shear, to denote double shear. Then the design of collar, again you can find this equation in the data handbook page number 67, 4.18a. Design of collar, again this is the area. So since it is hollow in cross section, the collar will be hollow in cross section. D2 square minus D1 square is used. Pi by 4 into outside diameter square minus inside diameter square is the area, multiplied by the stress. Type of stress will be compressive stress in the collar. Calculate D2, the corresponding dimension of the quarter joint. Then again that collar will be subjected to shear stress. For that, this will be the area of shear, pi into D1 into T. Here pi into D1 is the circumference, pi d is the circumference multiplied by the thickness or multiplied by the length, you will get the area of shear. Okay. From this you can able to calculate T1. Then in the step 5, design of the sleeve or the socket. Again here the sleeve or the socket will be in tension. Considering the tension, P is equal to pi by 4 into, this is capital D1 square minus small d1 square minus capital D1 minus small d1 into T into sigma T, where this entire term will be the area. From here to here, is the area. Okay, how this area is going to evolve? You just have a look at the figure shown in the previous slide. Okay, you can just compare with the figure, you can able to get the area. Here it is P, load is equal to area into the stress. Thereby you can able to calculate capital D1. Again you are going to find this equation in the page number 67, equation number 4.17a. Then P is equal to D1, D minus D1 into T into sigma C. Considering the compression of sleeve or the socket, compression in the sleeve or the socket, considering the compressive stress, try to calculate the diameter capital D. Then design of the socket end, for the shear. For the shear, this is the formula, you can find it in the equation 4.16g. Calculate the length of the socket. Calculate the length of the socket using this formula. Then at the end, design of the rod end, again for the shear. This is the formula to calculate design of the rod end, where this will be the area, this will be the stress, load. So area of shear multiplied by the shear stress is equal to load. So similarly, this is area of shear. Since it is double shear, it is 2. Area of shear stress, load. Okay. So basic formula being P, the load, is equal to area into the stress. The type of area, if it is shear, then take the corresponding area of shear. If the type of area is tearing, that is tensile, take the tensile area. Or the type of stress is the compressive stress, take the corresponding area which is undergoing compression. That is how the equations or the formulas are evolved. This is one type of designing for the cotter joint, okay, using the formulas. Another type of design is there. You can also follow the second type, where if you just have your data handbook, if you just open your data handbook and if you just go to page number 66, so here you can find the figure of the cotter joint. This is the figure of the cotter joint, and the dimensions are written here: D, T, D1, S, L, and all is written here, the corresponding dimensions. Okay, and just beside that figure, a table is given. Look at the table in the 66, you can just observe the table. So in this table, every dimensions, that is diameter of the rod end, small d1, thickness of the cotter, small t, width of the cotter, capital B or small b, diameter of the socket, d, whatever dimension we calculated using these formulas are written here, the dimension, and those dimension you can also able to calculate using the diameter of the rod to be joined between the two rods. Okay, diameter of the rod to be joined, that is this one. If we can calculate the diameter of the rod on either side using this particular diameter, if you just substitute that diameter here, that is for diameter of the rod end 1.25 times d. Similarly, thickness of the cotter t, if you want to calculate t, just substitute 0.25 into d1. Okay, you can able to calculate d1. Like that, if you just substitute for these empirical formula relations given in the table, the d calculated, you can able to calculate all these things without the formula. Okay, then if you try to calculate the dimensions using these empirical relations, then you have to recommend whether the design is safe or not. For that, again you need to go with the same equations, then try to substitute in this equation the calculated d1, the calculated t and calculated p, given p, try to compare with the stress. Then similarly here b and t you can able to calculate using the empirical relations by substituting in terms of D. Then try to substitute here P, B and T, calculate the shear stress. Compare this shear stress with the given shear stress in the problem or the shear stress of the material. If this exceeds that one, then the material is going to fail. If this shear stress, the developed shear stress will be less than the given stress, then it will be safe. Similarly, substitute for all the dimensions, try to calculate compressive stress, then compare this compressive stress with the given compressive stress of the material. If this is more than that, then the member will be a failure. If this is less than that, then the member will be a safer one. So like this is one of the method you can adopt. Okay. First step, you need to calculate the diameter of the rod to be joined. Then using the empirical relationship given in the page number 66 of data handbook, calculate all other dimensions like D1, T, L and all, calculate all other dimension, capital D, capital D1. Then try to substitute in these equations, get the stresses, shear stress, compressive stress and all, compare with the given set of stress in the problem. If that is more, if the developed stress is more than the given stress, then the member is going to be a failure. If the developed stress is well within the stress given in the problem for the material, then the design will be a safer one. So this is how you can able to calculate or the design a quarter joint using another method, or you can simply follow this method. Here there is no need to compare the stresses because you have already substituted in this formula and you have calculated the dimensions. Okay, you can follow both the options. There are two different ways of designing for quarter joint as well as in the knuckle joint. In the knuckle joint also you can find empirical relationship. Using those relationship you can calculate the dimensions, then substituting that dimension, calculating the stress developed, comparing with the given stress, and recommend the stress, the design is going to be a safe or a failure. This is what you can able to do. So this is general procedure to be followed by designing a quarter joint.